Our guest speaker tonight is Professor Alfonso Aragón-Salamanca. Alfonso was born in Spain, studied at the University of Madrid, and gained a PhD at Durham University. He is an astrophysicist and researcher primarily in the fields of extragalactic astronomy and observational cosmology, with the aim of explaining how galaxies form and evolve in different environments. He was a research fellow at the Institute of Astronomy, University of Cambridge, until 1999, then moved to the University of Nottingham as a lecturer. He was appointed as Professor of Astronomy in 2009 and is currently the head of Nottingham Astronomy Group. His talk this evening is entitled The Cosmic Web. He has visited and given talks to us many times before. So please give a warm welcome back to Professor Alfonso
Alfonso will do. Alfonso. Thank you very much. I think it's been recorded already, and it's a pleasure as always being here. And I'm going to talk to you about some of the work that I do precisely or linking the cosmic web, the large-scale structure of the universe, to galaxies, how galaxies form and evolve. Unfortunately, this is going to be only the first half of the story, because the story is kind of only halfway through. We've been working on this project for the last 12 years or so, and now, as we speak, the instrument is being commissioned, and we will start getting the science done from the next couple of months. But I will tell you what we want to do, what we plan to learn, and how we were trying to get there. And eventually, in 4 or 5 years' time, when we finish the project, I hope you invite me again and I'll tell you what we found out. But it is all about the cosmic web. If we look at how galaxies, how matter is distributed in the universe, is not nicely homogeneous and all sort of the same number of galaxies everywhere, but galaxies are distributed on a very interesting pattern that looks a little bit like a web, as we call it, the cosmic web. This is a computer simulation here in the middle, but what we want to do is to observe it, to see whether what the computer predicts and what we actually find agrees and what we can learn from that. And the new instrument in La Palma, this telescope here, is the William Herschel telescope, a 4-meter telescope, not a very large telescope, but if you put a good instrument on it, you can do state-of-the-art good science. And it's on the island of La Palma. And this is this outline of the island of La Palma in the Canary Islands, made out of fiber optics with the instrument that we're going to be used. I'll explain what that is in a minute. But we've known from the 80s, 1980s, that is not 1880s, I'm not that old, that when you look at how galaxies are distributed in the universe, and this was done in the Center for Astrophysics in Harvard, they measured the positions on the sky and the distances to give or take 1,000 galaxies. And when they plotted them, and this is, distance, and this is position on the sky, they were completely astonished to discover that they were forming this structure like that. They're not, they were expecting this to be covered with dots, pretty much randomly distributed, but they're not. They form these large filamentary structures. This is the Coma cluster of galaxies there. And there are filaments and walls and structure that surprised astronomers very, very much. And you could see that with about 1,000 galaxies. Now, a few years moved on, and with the telescope in Australia, the Anglo-Australian telescope. They went on the order of 100,000 galaxies. I think there's about 120,000 galaxies, and they looked, and when they looked many more galaxies, the structure became more interesting, better defined, but it's nothing like homogeneous, right? You still have galaxies clumping in clusters, in big filaments, in big walls covering sky. That was you get with about 100,000 galaxies. Then major progress was made at the Sloan Digital Sky Survey. Sorry, this is distracting me, that doesn't bother. And again, done with a quite small telescope, 2.5 meter telescope. But the Sloan Digital Sky Survey is probably the most successful, I was going to say astronomical research collaboration, but I'm going to say scientific research collaboration ever. Comparable perhaps to the human genome sequencing collaboration throughout the world, joining hundreds of astronomers doing science. And the first thing that the Sloan Digital Sky Survey did, and I'm sure that many of you have heard of it, is take a picture of a large fraction of the sky, about a third of the sky. There are many million galaxies there. Every dot here is many galaxies. But just by taking a picture with this very large camera in different colors, again, that structure appeared on the sky. But it's just the image. If I want to get a map in 3 dimensions, I need to measure where galaxies are on the sky, but also how far away they are. And how do astronomers measure the distance to galaxies? Sorry, just went too fast. You take spectra. Basically, you measure the color, how much light the galaxy emits a different color, and this is what you get. And galaxies sometimes emit very strong light of particular colors. This is a color that is actually very in the ultraviolet. These are colors that are in the blue, these 3 big peaks, this line here in the red. And that allows us to measure how fast the galaxy is moving. Why? Because this line here comes from hydrogen, the same hydrogen that forms the water molecule. These lines here comes from oxygen, the same oxygen that we breathe. That means that if I know in the lab where these lines are, and I measure where they actually appear, that tells me how fast it is moving. It's the same way that when an ambulance comes to me, I hear the pitch going up, and I know that the ambulance is coming in my direction. And when it goes away, the pitch of the siren goes down, and I know the ambulance is going away. That is how radars work. When the police wants to find how fast you're moving, they send light to you. They know the color of that light, they measure it back, and that difference tells you how fast it is moving. If I know how fast the galaxy is moving, there is something called Hubble's law that tells me that the distance of the galaxy is just the number times the velocity. So if I measure how fast the galaxy is moving, I take a spectrum, and a spectrum is just taking how much the light coming from the galaxy appears at every color, how much light there is at every color. Then I can measure the distance to the galaxy. Now, the way it works at Sloan is that they literally, on metal plates, they plug fiber optics. Fiber optics is a tube made out of glass that takes light from one place and puts it in another. So if on the focal plane of the telescope, I put a big plate of about this size, and I drill holes in each location, and I plug a fiber optic where I know there is a galaxy. I can measure the light of the galaxies for many galaxies at the same time using a spectrograph like that. And you can see all these red things that are the fibers. So what Sloan did was to measure distance to galaxies, many at the same time, hundreds of galaxies at the same time. It allowed them to measure, I was talking about first 1,000 galaxies, then 100,000 galaxies, then well over 1 million galaxies. And they built a three-dimensional image of the universe. And in this animation, every single picture here is a real galaxy taken from that image. I show you that the first thing that Sloan did was to, let me just go back to the previous one and run it again. Taking pictures of actually billions of galaxies, and then taking measured distances to hundreds of thousands, to actually well over 1 million of these galaxies. And what they saw when they put all those pictures in the right place at the right distance, that the universe again has got in 3 dimensions this filamentary structure that we call the cosmic web. So that is how Sloan did it. Of course, this strange structure of the piece is because obviously Sloan doesn't observe everywhere. Our own galaxy is in the way, so there are gaps. But in the regions where it looks at it, and I don't want to go that far back, I just want to go around here. That distribution of galaxies is not homogeneous. So now we have a very accurate map of the universe. We know where galaxies are, and this is just projected in 2 dimensions. But remember, we got this map in 3 dimensions. It's just a 3-dimensional map of the universe. And of course, these dots are many galaxies together, because here there are, as I said, about 1.2 million galaxies. So observers discovered that matter in the universe, and galaxies are like our own Milky Way, are sort of the building blocks of the universe, are not just randomly distributed. They are forming these very nice structures called the cosmic web. So we've observed that, and we need to explain it. How can we explain it? Okay, so the thing that you can do is to make sure that the computer works, and it goes to the next one. Okay, put in a, is that running? It is running. Build the universe in your computer. How do you do that? Well, you take a large computer and fill it with dots in which each dot is a bit of matter, a lump of matter. And then you just let gravity do the trick. What is gravity? Gravity is the force that binds us to the Earth, the force that gets the Earth running and orbiting the sun. Is the gravity is what keeps the sun orbit in the center of the galaxy. Is Newton's law of gravity. The equation for that law, we've known it for many centuries, and it's very simple. It's to just multiply the masses and divide it by the distance square, and you know how strong matter pulls to each other. But of course, if I want to do the calculation of the sun here and the Earth around it, that's very easy. I can do it on the back of an envelope because I've got only one body and another body. If I've got billions of bodies, billions of lumps of matter in the universe, then I need to calculate how this lump of matter attracts this one, but also how it attracts that one, and that one, and that one, and that one. And then once I calculate the forces, I see how all that matter moves within those forces. And when they did that in the computer, interestingly, they discovered that the universe in the computer looks very similar to the universe that we were observing. That cosmic web is there. So this is how the universe was a long time ago. This is a clock that is a long time ago, and Z means a long time ago. That is about, 12 billion years ago. That's about, say, 11. Then it will speed up. Now we're getting into probably, now it's 9, 8 billion years ago, 5 billion years ago, 4 billion years ago, 2 billion years ago, and that's how the universe is now. That is what Sloan says, that distribution, and it works very well, is very similar to what we were expecting. So, okay, I put matter in my computer and let it predict the universe, and it looks very similar to the universe that I see when I look on the sky. So this is still a universe in my computer, and it actually looks remarkably similar to the simulation, to the actual movie that I showed you before, were real pictures of galaxies. You see galaxies lumped in clusters that are connected through filaments. There are walls, there are lumps, small groups, bigger groups, large filaments that form the cosmic web. So the computer is able to calculate that with the simplest law of physics that I can put together, which is Newton's law of gravity. I don't even need Einstein for this. Newton does the trick. I just put that in the computer and I can predict exactly the existence of the cosmic web. Where does, what do I find? What I find, let's go back again. That, what do I find in the universe? Well, I find individual galaxies. And then I find that sometimes the galaxies lump themselves together in groups. They're together here, several galaxies together in a single group. Those groups are linked to other groups through filaments. Sometimes they're actually real walls of galaxies. Look at this enormous cluster of galaxies, gigantic cluster of galaxies, many hundreds of thousands of galaxies. Every lump here is a galaxy linked together with filaments. But that's interesting, but it doesn't really explain to me why that happens. The computer calculates it with the physics, but doesn't tell me why that is actually happening. And the creation of these structures appears in many areas of physics. It appears in the cosmic web, it appears in gas in our own galaxy, it appears in radio structures in the universe. Why do we get these structures that can be large lumps of matter, filaments, or walls? Well, it's very simple. Imagine I've got here a region of the universe in which I start with the matter distributed completely homogeneously. There's the same number of dots everywhere, approximately, maybe 10 dots in every circle. That's fine. And you say, how do I get from there to a structure that is so interesting and so complicated? What's the physics? If I put it in the computer tells me, yes, that's what you get. I let gravity act and I get that. Well, it's very simple. It is called gravitational instability. That doesn't mean anything, does it? No. Exactly. What it means is that the gravity is greedy. The more it gets, the more it wants. So imagine I've got this distribution of matter that is completely homogeneous, but it will never be completely homogeneous, right? There will be a region in which there are perhaps 3 dots more than in another region, right? So that means that it's got a little bit more mass, a little bit more matter. But if you remember, Newton tells me that to calculate the force between 2 bodies, I need to multiply the masses divided by the distance squared. So if I've got a little bit more matter together, then it will have a bit of a stronger gravity than the region next to it has got a little bit less matter. So imagine that in this region, I've got 20 lumps of matter, and in the region next to it, I've got only 18. What's going to happen? That the region that's got 20 is stronger than the region that is 18. It will pull matter from the region that is 18 and become even bigger. The region that is bigger pulls more matter, becomes even bigger, and the region that is weaker, that's got less matter, becomes weaker. So that's like real life, right? If you're very rich, you get more at the expense of the people who are poor. We know that, but that's what happens with gravity. It's also greedy. the more it gets, the more it grows. And the less it has, the more it loses. So now that explains how if I've got a region that has got more matter, yeah, it's going to pull more matter and grow, right? And everything will be trying to fall towards the center. If I've got something that is perfectly round, perfectly spherical, it will go and collapse spherically, and it just be, because gravity pulls things to the center, and it will collapse on itself. But perfection never happens, right? Nothing, nobody is perfect. So it will never be a perfect sphere. It will be a direction in which is slightly shorter than another, just a little bit, maybe 1% shorter. So you look at it and it looks perfectly spherical, perfectly round, but it's slightly shorter in one direction. Now, in Newton's law, it tells me that the force goes down with distance. So when distance is smaller, the force is stronger. So in the region in which it was squashed a little bit, that sphere was not perfectly round, it was squashed a little bit. The distance is smaller, the force will be bigger. So that region will be pulling inwards a bit faster than the region from the other side, because on the other region, the distance was slightly bigger, right? You only need a small squash in one direction, and that will grow. So something that was almost perfectly spherical, if in one direction was slightly smaller, it will collapse faster and become more and more and more squashed. So I'll start with a big sphere and you'll end up with a pancake, right? Does that make sense?
Yeah.
Good. But is my pancake perfectly round? No. In one direction, maybe 1% slightly more squashed. Now you see the end of the story, right? You can see that in the direction in which is a bit more squashed, it will collapse on itself and form a filament, right? The sphere collapses into a pancake, and in the direction in which the pancake was slightly squashed, it will collapse faster and form a filament. So that is how, and then after a while, that filament will all collapse into a lump, into a cluster. So now we've got everything we wanted, right? Let's just go back. Here, okay, let's see what we want to start. Doesn't want to run. Come on, my friend. Just trying to do too many things. We can look at it easier. So if we catch something when it starts, it's completely collapsed. So doesn't want to do it. Okay, now it does. So if I catch something when it's starting to collapse, it's very large and it's very homogeneous. But if I catch something when it's in the pancake state, I've got like a wall of matter. If I catch something when it's going into a filament, I've got a filament. If I catch something that has gone all the way into a cluster, I get a cluster. So in the universe, just this very simple physics explain why I can get from clusters, which is the end product of the whole collapse. I can get a filament, which is I'm almost there. I can get a pancake, or I can get matter everywhere. So in the universe, depending on when I catch a region of space, I can have all these structures. I can have the final collapse, which is the cluster. I can have the filament. It normally will be linking one cluster with another. I can have the wall of matter. And that is the cosmic web. So let's recap. Astronomers discovered that matter is distributed in that way. There is filaments, there are walls, there are clusters. We put simple physics, Newton's law of gravity, in a computer, and it gets us the same structure. There it is, that's a computer simulation. But I don't like just putting something in a computer and a computer gives me the answer. I want to understand it. And I think I've explained to you using this gravitational instability, or gravity is greedy. we can explain why we find clusters, filaments, pancakes that are works. So that simple physics explains how all these things work. Why does this interest me? This interests me because I am interested in what environment does to galaxies. Right? We know that the environment affects how people live, right? Somebody who lives in the center of London does not have the same kind of life as somebody who lives in the middle of the desert, or somebody who lives in the middle of Yorkshire Moors, right? Where you live affects your life, affects the life, your health, affects your wealth, affects what you like. So environment affects how people live. The same with galaxies. Environment affects how galaxies form, how galaxies evolve. And so if we look in the universe, in this pie chart, most of the universe is empty. You see what we call voids, regions where there are very few galaxies. A little bit of it is in walls. I talked about the walls. A little bit of it is the volume is in filaments, and a little bit in the nodes or clusters. But that's the volume. If we look at where galaxies live, galaxies mostly live in what we call filaments, in those long strands of matter. More than half of the galaxies, or about half of the galaxies, live there. About 24% live in walls, and 11% lives in those clusters, and only 15% lives in those voids. That is what attracted and made me very interested in filaments of galaxies. And why did I get interested in that? Because for many years, I've been interested in clusters of galaxies, the things, the nodes, the lumps in the middle, the spherical regions like this, with many galaxies together. And what I've been studying for many years is that the properties of galaxies in these clusters depend on where they are. And sorry, there is a plot here, but it's not very difficult to understand. This is the fraction of the different types of galaxies. And you know that galaxies can be spirals, can be lenticulars, can be ellipticals. They've got different shapes. What we find is that if I'm in a region where there are very few galaxies, this is a region with low density, an empty region, the vast majority of my galaxies are spirals or irregulars. And I've got very few ellipticals or lenticulars. But if I go to the center of clusters, this is the coma cluster of galaxies, more than half of my galaxies become lenticulars or ellipticals, and I've got very few spirals and irregulars. So it's quite clear that if I live alone, and I'm a galaxy, I'm probably a spiral galaxy. If I live with many people, I'm probably a lenticular or an elliptical galaxy. So what makes a galaxy change? Why does a galaxy know where it lives? Okay, a galaxy that today is in a cluster, this simulation of a cluster over time is an old simulation, but I like it. At the beginning of time, the universe was expanding. We know that the universe is expanding. And so matter was getting farther and farther away. And all these galaxies were getting farther and farther away. And when they were very far away, what were they? Probably spirals, right? Because they lived far away. But at some point, gravity wins and starts pulling them back together, and they start falling down into a cluster. So all these galaxies that when they were far away were nice spiral galaxies, they fall onto the cluster and they become elliptical galaxies. So in the process of falling into the cluster, something happens to the galaxies and changes these properties. So that in the cluster, this galaxy that before, when it was very far away, was a nice spiral galaxy, by the time they come here 1 billion years later, it's become an elliptical galaxy. So we don't understand that process of what the environment does. So if you look at this is the Virgo cluster of galaxies. Again, each one of these galaxies is a real picture of a galaxy in the Virgo cluster, and they move according to the velocities we measure. And so interestingly, as you can see, galaxies in a cluster are moving past each other very fast, 1,000 kilometers a second, 600 kilometers a second. And in these interactions, many things can happen. Many things can happen. I'm going to just mention one. When galaxies are in a region that is crowded, they can collide with each other, okay? And they can, and just run it, they can collide with each other and then merge. And then again, here is a simulation in which I've got a galaxy in my computer, which is a nice spiral galaxy. And then, then they are approaching each other. Okay, so this is a real simulation in the beginning. This is the simulation, and then I can find what happens to the galaxy later. They're getting closer, and I see galaxies in the universe that look like that. This is a real picture of a galaxy. A real picture of a galaxy, simulation. Let's see what happens a bit later. Interesting stuff, right? The galaxies get completely messed up when they collide with each other, and I get galaxies in the universe that look like that. So see, there's always a simulation in the computer, and then afterwards, a real galaxy. We just rotate it, look at it from another angle, and they're real galaxies like. So what this simulation shows is that if I'm in a region in which I can interact with other galaxies, I can collide with them, interesting stuff will happen to me, okay? Interesting stuff will happen to me, and in the end, I will not look anything like what I looked at the beginning. And that depends very much on where I am, okay? So if I'm in a region in which I'm alone, the chances of me banging into somebody else are very small. If I'm in a region in which there are many other galaxies, the chances of me banging with somebody else, if I'm walking the streets of London, I end up always banging into people. But if I'm walking in the Yorkshire Moors, the chances are that I don't bump into anybody. The important thing that I want to take home here is the idea that depending on where I am, what happens to me changes. And that's what happens with galaxies. So depending on the environment, on the different environments that I consider, galaxies will be different. I'm gonna move on from here. So from an individual galaxy to what happens when I'm in a cluster, or what happens when I'm in a filament or in a void, my properties will change. So we don't really know very well what is happening in these environments. We don't really know how many galaxies collide with each other, how many galaxies merge, how many galaxies they just pass very fast next to each other and the matter gets pulled apart. And if we want to learn that, we need to explore all these environments. And I showed you before that about half of the galaxies are in this very interesting environment. Let's just go back to that pie chart. I can find it, which is just before this one. Who wants to? Someone to? Then the next one. The computer is trying to do too many things. Here, you see, I want to know how many galaxies in reality, because this is in my computer, how many galaxies live in walls, how many galaxies live in filaments, how many galaxies live in nodes that I've been calling clusters, how many galaxies live in voids, and I want to identify them. I want to say, this galaxy that I'm studying now is in a filament. This galaxy that I'm studying now is in a cluster. Why? Because then I can look at the properties and try to understand what transformation happens. Okay. I don't really know what happens, and that is what we're trying to learn. So what I want to do, what this project that we want to do is about is doing a census of galaxies. The same way that every 10 years in this country we get a census that counts how many people live in each town, in each village, in each street, how many people are tall, or what age they have, all the properties. That's exactly what sorry. It's a Buzz Aldrin or something. Yeah, sorry, Buzz. Before I study how galaxies change, I need to do the homework. I need to do the census. I need to find the galaxies in a particular location and measure the properties. And I want to do it not with 10 or 20, because then, you know, if I've got a very small sample, I may be missing galaxies. I will not be able to say, okay, on average, in Mansfield, people are 2 inches taller than people that live in, say, Burkina Faso in Africa, right? That kind of information I need before I can study it, and I want it with many galaxies. So this is, and then now we can move on forward to the actual project that I want to talk about. So now I hope I've convinced you that it is important to learn where galaxies are in this cosmic web, to do the census so that we can learn what influences them. How many big galaxies, how many small galaxies, how many galaxies forming stars, how many galaxies are not forming stars, how many galaxies are spirals, how many galaxies are ellipticals. But in order to do that and do it well, we need to get observations, okay? We got here in the simulation on the right hand, if it works, I'll keep running, right? But that simulation, which is similar to what I've shown you before now, colored green, that is the same thing. I want to see whether what I observe with the telescope matches the simulations, but I want to learn more, because by the simulations, they do not tell me what kind of galaxies I get and what happens to those galaxies. So the observations that we're going to do from what we call the WIV wide cluster survey. WIV is the name of the instrument that we've been working on for the last, I think, 12, 14 years, and is now on the telescope of La Palma. And I tell you a little bit on what we want to do. I told you before that Sloan took metal plates, drilled holes in them, and plugged by hand fiber optics. And fiber optics are what we need to take the light from each galaxy, put it in the spectrograph, that instrument that measures 2 things. One is how far away that galaxy is, and also what it is made of, what kind of stars it has, how many stars it has. Sloan did it by hand, a few hundred at a time. What this instrument does, it has about 1,000 fibers. So this here is a metal plate on the focal plane of the telescope, and what each square here is a prism. So light is coming from the telescope into each one of these positions. Each galaxy, each one of these buttons is placed on the position of a galaxy. So the light comes onto these buttons, and these buttons have got a prism. So the light that comes this way is sent at 90 degrees, is channeled through all of these fiber optics, and those are taken to the spectrograph. So basically, all of these fiber optics are pipes of light, but because I don't want to drill this plate, and I'll show you why not in a minute, I don't want to have a hole at the back and plug the fiber optics so that the light goes directly through it. Each fiber optics is plugged onto a prism, so light comes this way, is sent this way, down the fiber optic, all the way to the spectrograph. And these are tens of meters long, all these fibers. This thing is of the order of about 1 meter in diameter. We'll see it in a minute. So reverse again. This is a simulation of a cluster of galaxies. Here I've got the center of my cluster, the high density, the center of London, but I've also seen the regions with low density, and I can see those filaments. So we're gonna do, because I want many galaxies, I point this 1, 2, 3, 4, 5, 6, 7 times. Each one of these pointings, each time I point one of these things there. Come on. Now it's gone too fast. You see, I'm going to put this in all these locations around regions of the sky that contain a cluster. And so I get 1,000 galaxies here and 1,000 galaxies here and 1,000 galaxies here. And I'm going to end up having between 8 and 10,000 galaxies for each one of these structures. And for each galaxy, I'll measure where it is. I'll measure the distance, I'll measure the position, so I will know the geography, I'll do the census. But I will also learn for each galaxy lots of things. How many stars is it forming? What chemical composition? What is it made of? Is it an old galaxy? Are all the stars young stars? So I will put together the census information, the geography, where the galaxies are, with the properties, so that I will be able to learn what is making these galaxies be the way they are. And so this is what we want to do with Weave, right? So Weave is this instrument that this is real fiber. So this is the fiber. So I've got my prism here. Well, let's just pretend that it's prism. So this gets stuck on the metal plate. It's got a little magnet, and then the fiber comes outside, is kept under tension. So that's why they are nice and straight. And the light comes here, gets sent to the side, goes through that pipe, that fiber optics, go to the spectrograph that does the measurement for me. And here what we did was to draw the island of La Palma in those days. And it's a long road to Weave. Weave is the name of the spectrograph, which I can't even remember what it stands for. It's something like wide something, something, something. It doesn't matter, it's an interesting instrument. But these are these telescopes. And this is the actual road to La Palma, and it was a long road, and it's often icy. So the instrument goes on the prime focus of the telescope. So you got the telescope that will see there, and it's at the prime focus of the telescope. So this is pointing downwards. So the light from the telescope comes, and here is a plate, that plate, and all the fibers come out and go round that circle and then go down to the telescope. But we are greedy, a little bit like gravity, and instead of having one single plate, we've got two. You will see later that all these fibers are put in place by a robot. I'll show you the robot that goes It takes about an hour to configure 1,000 of those. And it takes about an hour of exposure time to take the data. So I can just, if I've got only one plate, I've got to twiddle my thumbs for 1 hour, waste 1 hour of good night time. So no, I'm not going to do that. This whole thing tumbles. So the top, the robot is positioned in my next observing field. Well, I'm observing the one that it was positioned before. So at the top, I've got this thing putting the fibers in the right place to observe the right galaxies, while I'm observing the ones that I configured before. 1 hour later, I've taken my data, I tumble the whole thing, so it takes about 3 minutes, and I take another observation. Okay, so I've got two of those robots, two of those plates, and let's just see. And this is just to show that how complex it is. So this is Gavin, the instrument scientist, Gavin Dalton. This is the plate that I showed you before, where the fibers are. This is one end. This is the William Hertz telescope. The primary mirror is there actually covered with the coverage on the side. We don't observe with the telescope on the side, but that's how you get access to it. And that tells you it's about 1 meter or so in diameter. And then that's at the other end of the telescope. We're looking at it from underneath, from as it were, the primary mirror. There are big lenses there because you need to correct the optics. And here it is. This is the primary mirror of the telescope. This is the primary focus. Here is the complex optics that gets the light nice and focused. And then you got here at the top, the robot configuring one observation while it can point out, of course, this is daytime, but that's not when it's observing. So all the 1,000 fibers are there, then they come down through those, some of those trusses into all those 1,000 fibers are real. And then let's see whether we can see how it actually works. That is the configured plate. You can see it doesn't, it's a bit out of focus here, or it's just the resolution not very good. So each one of these things is something that is got a little bit of a reel that keeps those fibers in tension. Of course, you don't want the fibers to be all dangling and getting in the way. So all of these things are magnetic. This is a steel plate. And so these things get there. They are in one position and you got the other, but I want to show you how it actually looks. It's a big thing, about a meter side. You can see all those, only a few fibers are configured there, but you can configure 1,000. And they are configured by the robot. You can see how it picks up one of those things. And in fact, there are 2 robots, because if not, it would take 2 hours. And because it takes about 1 hour. So you can see this is, of course, not on the telescope, it's in a lab in Oxford where it was put together. These things are just a magnetic button, gets stuck to the plate, so that when the plate goes upside down, so that you look into the primary mirror, they don't fall, and all of these are kept under tension. Okay, so this is about 1/3 of the real speed. This is where they were testing it all the time. So you can run about 3 times faster than that. So you can do, because 1,000 fibers. Can you imagine also the programming that goes into, okay, I've got my list of galaxies and I've got the coordinates. I know where I've got to point, but what is the best configuration of fibers? How do I do it so that I don't cross too many fibers? That I've had my fibers in a position, but then for the next place, I need to move them to a different location. What is the best way to do that without that entangling all the fibers and breaking it? Just the logistics and the complexity of that is interesting. Anyway, this is a complex instrument. This is what it looks like in the computer, and this is what it looks like in real life. This is the spectrograph. All those fibers take the light, 1,000 of those. They are pipes of light. You take them to the spectrograph. The spectrograph has got lenses. It's got similar things to prisms that basically take the light, white light, and make the rainbow. And then we measure each rainbow for each galaxy. And we take the data home and we analyze it. Or we will eventually, when we look at these clusters, and what we want to do is to map. I remind you, I want to see which galaxies are in this region, in this filament, in this void. Once I've got my census, when I've got the properties of galaxies, we'll do science with them. That is what we're going to do. I think this is the timeline. I remember a kickoff meeting in September 2011 in Schiphol Airport, the Netherlands. This was pre-Zoom and pre-pandemic, so people got together into a place. What was the easiest place in Europe to get European astronomers? Schiphol Airport in Amsterdam is the cheapest way to fly. Just can fly there from any airport, because these join astronomers in Spain, in the Netherlands, in Italy, and now people have joined us from Italy and Germany as well. So there we got together and said, well, this is what we want to have. This instrument, I wanted to study the cosmic world. Other people wanted to study stars. Other people wanted to study quasars. Other people wanted to study, why not, right? So we said, okay, the same instrument can do all these things. So then in 2011, we put together the science case where we said what we wanted to do. Preliminary design, so somebody took a piece of paper and said, well, we want all these fibers, we want a spectrogram here. Preliminary design, March 2013. Then we got the money, and then the first light happened last winter. Commissioning is happening now, and the service will start later this year. And it's been a long and icy road. Everything that could happen has happened. We had a pandemic, we had a volcano, we had the lot. So we are about 3 years late. 2 years due to the pandemic, because nobody could go to La Palma when the instrument was pretty much finished in Oslo. Nobody could take it to La Palma. When they could take it to La Palma, the volcano went. So hopefully it will work. Now I'm going to show you that we are getting real light. And this is actually from another version of the instrument. No, another part of the instrument in which instead of having all your fiber optics one in different location, you just get them all together, packed together into a hexagon, and then you get a spectra of each position in each galaxy. That was done in what is called first light. So the first object that was observed was the Stephan's quartet. So we just put Stephan's quintet, and so we just put the spectrograph in such a way in which all the fibers were packed together. In fact, it's a different set of fibers. Okay, but just to show you that we've got light, we observed this very interesting set of merging galaxies that interest me because that will tell me what happens when galaxies interact with each other. Okay, and we obtain data that we're still analyzing, and a paper will come. Gone too far. Data that we are analyzing now. It needs to be set to run. And what we're going to be seeing is light from, this is light obtained with this spectrograph in which the different colors tells us different information. So we've got maps here that tells us how hot the material is, how fast the material is moving, what it's made of, etc. So all that information is encoded there in this sort of animation, and we are trying to extract it for this particular object. Okay? This is not the kind of data that I'm going to be working with, because what I want is just many galaxies. This is a few galaxies in great detail, but you can also study many galaxies in less detail, which is what I'm going to do. As I said, we expect this to start September, maybe October this year. We've got about 5 years. By the end of those 5 years, I want to have about 20 regions of the sky that contain a cluster in the middle and the cosmic web around it. In each one of those, I'll get 10,000 spectra. And we will be analyzing all that information to learn how galaxies form and evolve in all these different environments. And I cannot give you the answer because I haven't done the experiment yet, right? So what I'm going to say, invite me in 5 years' time, and I will tell you the answer. I'm not finished.